Okay, so I'm going to work through question 2, the 2009 Chemmat 312 exam. If you haven't already had a look at the paper, I recommend going and printing it off now because I'm going to refer to it quite heavily during this question. So to start off, we have a 2,850 kilograms of meal coming into our system, and this 2,850 kilograms consists of 800 kilograms of oil, so that's our component A, because that's what we're trying to extract. It comes with 50 kilograms of solvent, so that's going to be C, and then the remainder is going to be our inert solid, that's going to be our B, so that's going to be 2,000. That's just a simple mass balance. Now, looking at the question, it's asking us to figure out the number of ideal stages. So we can be pretty confident this isn't going to be a single stage process, and as a result it's going to be multiple stages to consider. So let's label this as our first stage, and then let's simply draw a box around the rest of the stages, and let's just say that's n-1 stages. And then let's just draw in the rest of the arrows. We've got our underflow streams carrying our solid through the bottom, and then we've got our overflow streams with our solvent coming through the top. Okay, so what else do we know? We've done our solid coming in, so that's going to be L0. That's our underflow stream coming in. What else do we know? We know that the solvent there is 1,330 kilograms an hour, and that's 1.5% oil. So simply by taking percentages, we can say that that consists of about 20 kilograms of oil, and the remainder, so the other 98.5%, that's going to be our solvent. Cool. So far, so good. We also know that the exhausted solids are to contain no more than 120 kilograms of unextracted oil. So we can say A down here is going to be 120 kilograms. We also know that the solid coming in is going to equal the solid coming out. So this is going to be 2,000, and it's worth noting that there's going to be no solid up in this overflow region. All the solid's going to stay in this underflow, sort of by definition, if you like. Okay, and then simply by doing a mass balance on component A, you can see we've got 800 coming in here, 20 coming in here, and then 120 coming out. So the rest of component A is going to be up here, and this is going to be equal to 700, just a simple mass balance. Let's go ahead and label all these streams now, before we forget. So I've done L0, that's done. This is our overflow stream coming out of the first stage. So that's going to be V1, V for overflow, and then 1 because it's coming out of stage 1. This one up here, this is also an overflow stream, so it's going to be B. And it's coming from the stage after the nth stage, so it's going to be Vn plus 1. And then finally this stream down here, that's going to be L because it's an underflow, and it's coming out of stage N, so that's going to be Ln. And then if you like, we can go ahead and label these intermediate streams here. So that's going to be Vn, and that's going to be L1. So the first part of the question asks us to calculate the concentration of the solution retained by the extracted solid. So that's going to be down here. It's going to be this concentration down here. For the moment, we know the amount of oil, and we know the amount of solid. We don't know the amount of solvent, so we can't we can't simply solve for that straight away. So what we've been given is a table which gives the concentration of the oil, and that links it to the ratio of solution retained to the mass of inert solid. And if you look at that right hand side of the table, you can kind of see that that looks pretty similar to what we define as N. So let me just write it out. So N we defined as the mass of solid over the mass of solution. So actually, just by looking at that, we can see that what's given on the right hand side of the table is actually just equal to 1 over N. So if you like, we've sort of been given a relationship between concentration X and effectively the n value, we just need to do a quick flip the numbers over calculation. So as hinted in the question, the way to solve this is through iteration. So what I'm going to do is I'm going to do one sample iteration for you just to see what the process is like, and then you can go through and do it more accurately later on if you want, or you can just do what I did and just put it in Excel and see what the answer is. So we're given a relationship between x and this ratio of solution to solid. So let's just pick a random value. So the second one down in the table says that x is equal to 0.1, and I'm going to call this 1 over n because it's our solution to solid ratio, so it's effectively just the inverse of n, and that's going to be equal to 0.505. That's just straight off the table. So what we need to do now is we need to take this guess, if you like, work through the numbers and see if it all kind of checks out. And we can sort of tell from that whether or not our guess was any good to start with. So if we think of, if we have 1 over n is 0.505, we can say that n is going to be equal to 1 over that. So it's going to be 1.98. And then remember we defined n is equal to the mass of our solid, which is B, divided by the mass of our solution, which is Ln, if we're looking at the stream down here. So in this case, we actually know what B is. B is 2000. That's just the mass of our solid. That's constant throughout the whole thing. And we know n is 1.98 from our guess, so you can actually go ahead and calculate Ln if this guess is correct. So we can't just, go running off and solve the whole rest of the question. We've got to check to make sure our guess is correct first. So based on this calculation, Ln is going to be 1010. And now what we want to do is we were given what the concentration of X should, or the concentration of A should be. Let's go and figure out what it actually is, given the data that we've got. So we know that Ln equals 1010, and we know that in this stream there's going to be 120 kilograms of A. So therefore we can actually go ahead and write that Xn, or the concentration of A in our solid coming out, is going to be equal to 120 over 1010, and that's going to be equal to 0.118. And as we can see, that's pretty close to what the table suggests it should be, 0.1. So you can go ahead and iterate further. I did it on Excel earlier, and it turns out that your solution, X, is actually going to be 0.118. Let's move the paper up a little bit. And then, just remember what value of n that corresponded to. That corresponded to a value of n of 1.972. So the right hand side of the table would just be 1 over that. So it'd be about 0.5 something, pretty close to what we initially guessed. So now we've got that. Well, that's actually the answer to the part A of the question, because the part A of the question asked us what is the concentration of the solution retained by the extracted solid. That's exactly what we figured out. That's 0.118. So that is the answer to part A. And now that we've figured out this, actually parts B, C, and D are actually all pretty simple. It's just a little bit of mass balance going on. So let's work through each of those individually. So I get a new piece of paper out. So next thing to calculate is you want to figure out the concentration of the strong liquor. So the strong liquor is this up here. It's our overflow stream coming out. So now that we've got 700 kilograms of A, there's going to be no B in there, and there's going to be some solvent left over, which is not quite sure what that is at this stage. Let's do so. The solution is going to be to do a mass balance. So, given that we know what the concentration of the extracted solid was, we know it's 0.118, let's go ahead and use that and figure out what the actual Ln solution coming out is. So we know that n is equal to 1.972. That was sort of the result of our iteration process. So therefore, using the exact same thing we did earlier, we can say that 1.972 is equal to B, 2000, divided by Ln. And that's simply the definition of what n is. So using that, we can solve for Ln. That's going to be 1013.67. Remember when we did it with our first iteration, it was 1010. So again, we weren't actually too far off. Let's make sure you can see everything I'm doing. Okay, so we've got Ln. And that tells us the total amount of A and C that's in this stream here. So if we know, and we know from the question there's 120 kilograms of A in that stream, so therefore the amount of solvent in that stream, C, initially we didn't know that, now we can calculate that simply as sort of what's left over. So it's 1013.67 minus A, 120, and that gives us 893.67 kilograms. Why does that help us? Well, if we know C down here, we also know C here, we can do a material balance on our whole system. We can figure out the total amount of solution up in here, and then if we know the total amount of solution, we can figure out the concentration of component A. So let's go ahead and do that. So simply by doing a quick mass balance on C, we've got 1,310 kilograms coming in, plus 50 from our solid, minus 893.67 going out with our solid. That means that the remainder, 466.33, is going to be coming out in our overflow stream. So now we've got the mass of A, and we've got the mass of C, so we can actually go ahead and calculate the concentration of A in that stream. That's pretty simple. So all that is that's going to be Y1. It's going to be 700. Yeah, you can see what I'm doing, good. Over 700 plus 466.33. So that's going to be equal to 0.6, exactly. Usually a pretty good sign we're on the right track. So that's part B answered. Part C, the mass of solution retained by the extracted meal. So that is looking at, the extracted meal is going to be this solution down here. That's actually going to be Ln, which we've already calculated. So that was part B. C is simply asking us for what Ln is, and we already calculated that earlier. So that was 1013.67 kilograms. And then now for part D, the mass of the strong liquor. Again, we've basically already calculated that. It's just going to be A plus C, the total mass of solution in that strong liquor. So that's going to be V1, it's going to be equal to 700, so A plus 466.33. That's going to be our C. So our total solution is going to be 1,166.3 kilograms. So that is the whole part of the first part of this question finished. Unfortunately, that was the easy part. Part E is where things get a little bit more hairy. So I guess the first thing to think about when we're looking at the number of ideal stages is what method we're going to use. And because we were given a relationship between concentration X and N earlier on in the question, you can probably infer from that this isn't going to be a constant underflow process. It's going to be a variable underflow process because that N isn't going to stay constant. If it was constant, they wouldn't need to give us a big table showing us how it changes. So if it's a variable underflow process, the way to solve that's going to be the, I don't know how to pronounce it, the modified Ponch method something. So that's what we're going to try and do. So in order to do that, this is just sort of a quick schematic of what we're going to do. So we're going to have n up on the y-axis and then x on here. We're going to draw our n versus x relationship along here. We're going to find our L0 and midpoint, connect everything up, and then do a whole lot of graphy stuff. So in this exam paper, graph paper was provided, and what you need to do, really the key thing you need to do for this part of the question, part E, is you've got to have this this n versus x relationship, and this would be for your underflow condition. Remember, your overflow is just going to be down here, because if it's overflow, you've got no solid, so your n is always going to be 0. So we need to plot this relationship on graph paper. I've been lazy and I've done it on Excel, so I'm going to bring this one out. I did earlier. I'll rub everything out and start again, and then we'll have a work through it. Okay, we're back in business. So this is a plot of the n versus x curve, which I've done on Excel. I don't know how well you can see that. All I've done is simply plotted the table that was given in the exam question, except I converted that right hand side to n by just going 1 over it. So I've got n on the right hand side and then x on the x-axis. You could do this yourself on graph paper if you wanted to. I've just done it on Excel and then just put a line of best fit straight through it. Thought that was probably easier to do than doing it by hand. So when we're doing this modified method, there's a few things we need to calculate. It's quite a lot of different points we need to figure out. So let's go ahead and label the ones that we do know that are pretty obvious. So first point we need to plot is L0. That's our starting point. That's really, really important. So in this case, L0, we need to plot x0 and we need to plot n0. That's going to give us the location on this plot. So x0 is going to be the concentration of A in the solid coming in. So just simply by doing a really, really easy calculation, we can see that the concentration of A is going to be 800 divided by 850, so that's 800 plus 50. Remember, it's the concentration of A in the solution, so we're not worried about our B here. It's just A and C we're concerned about. So it's going to be 800 over 850. So that's going to give us 0.941. And then for N's going to be it's going to be the B, mass of solid, divided by the mass of solution. So that's going to be 2000, which is our B, that's constant. And then our mass of solution is going to be 800 plus 50, so 850. So N's going to be 2.35. And if I'll plot this roughly on the curve, I won't be too accurate. So 2.35 and 0.941 is going to be somewhere up here. That's going to be our L0 point. Okay, that's a start. Now the next step to do, well, the next thing we can do is we can plot our Vn point. So what our Vn point, that is, sorry, Vn plus 1 I should say, it's our overflow stream coming in. So that's sort of right at the opposite end of the process. So it's our other stream coming in, right at the other end of the process. So in this case, we need to figure out, again, the logic is exactly the same. We're going to plot xn plus 1, and we're going to plot n plus 1. So again, we need to figure out the concentration of A in this stream. So we've got 20 kilograms over 1,330 kilograms, and that was actually given to us in the question. It was 0.0105, or 1.5%. And then N, or for this case, N's actually going to be 0, right? Because it's an overflow stream. We don't have any solid at all. So this one's actually going to lie on the y-axis. So if we plot that one in, I should say it's like going to lie on the x-axis. It's going to lie about here, so it's just across. I'll just scroll up a bit. Just across from our origin, and we know that L0, our starting point, and our Vm plus 1, they're going to lie along a straight line. They're going to be connected together. So I'm just going to get a ruler and I'm going to connect those two together. Simply just joining the dots like that. I hope you can see this. You'd waste time otherwise. So I've just connected the dots there. Okay, I'll try and keep that visible. Now, there's going to be an M point at some point along this line. We don't quite know where that is yet. And there's two ways of going about that. We can either calculate it using what's called the lever rule and actually measure it based on the length of the lines and the ratio of the two streams. I think in this case it's probably easier just to calculate it numerically, so I'm just going to go ahead and do that. Feel free to work through the lever rule and check it in your own time. So, what's M? M is basically just the total amount of solution in the system at any one time. So let's take the L0 and the Vm. So let's take our inlet streams and figure out how much solution is coming through. So we've got 800 up here, plus 50 coming in our solid, and then we've got plus 20, plus 13, 1,310 coming up in our solvent. So M is going to be 2,180 kilograms. So that's the total amount of solution in our process at any one time, and that's going to stay constant. So that's why calculating this is quite important. The next step is to figure out the concentration of component A in this mixed solution. That's sort of like the average. You can sort of think of it the average concentration of component A. So go ahead and do that. The total amount of A in the system at one time is going to be 800 here plus 20. So 820 divided by the total mass of solution, which is 2,180. So that's going to give us 0.376. So that's going to give us the x coordinate. So it's going to be somewhere along here in our graph. This is very difficult. Bear with me. And then the next step is to figure out the n at this midpoint. So this is pretty simple. Nm is equal to the mass of solid. So that's, again, 2,000. That hasn't changed. Divided by our mass of solution, which is 2,180. So it's just B over M. That's equal to 2,000 divided by 2,180. So N is going to be 0.917. So if I plot that onto the graph, it's going to give us an endpoint around here. And if you'd used the lever rule, you'd have found out that that would have given you roughly the same answer, I hope. So that's our endpoint. Now what do we do from here? The next step is to figure out our Ln point. So what we've done so far is we've plotted this and this. We've plotted our two inlet streams. Now let's go and plot our two outlet streams and let's sort of see the relationship between them. So we can start with Ln because we know a little bit about that. We worked with that one earlier. Let me just grab some more paper. Just try and keep that roughly. Just try and put that up there. Cool. Okay, Ln stream. So that's our extracted solid coming out. So we are looking for, again, we're looking for x, n, and we're looking for n, n. So xn, that's actually what we calculated way back in part 1. So we calculated that as 0.118. And nn, again, that was also what we calculated way back in part 1. It was this bit, this number down here, 1.972. That's going to be 1.972. So you can kind of see that instead of doing all that iteration way back in part A, we could have actually solved it graphically, and that was something that Wei worked through in one of the lectures, and you can sort of see how that arose. So instead of doing iteration, if we plotted it and instead solved it graphically, that's also another way to have done it. And we can sort of see that here, but we'll just continue with what we've done so far. So we can plot in, sorry, my computer's gone off. Go back to our graph, we can plot in our ln point, so that's going to be up here, using the coordinates we've established. And we know that ln and m are going to form a straight line. And when they connect to where they hit the bottom, that's going to give us our V1 point. So that's going to be our other outlet stream up here. So let me just draw those two together, connect those two together. Okay. So we've now got ln, V1, Vn plus 1 and L0. So it's all we've got our inlet streams and our outlet streams. That's actually really, well, that's probably the hardest bit done. That's probably the hardest bit. The next bit is to figure out our pinch point. And we can do that by simply drawing a line between L0 and V1. So let me just do that. I'm going to take a massive line all the way across the page. And of course it goes off the page. And then between ln and vn plus 1, we're going to draw another line, and then we're going to figure out where they connect. Unfortunately, I don't know how well you can see this, they are not quite going to connect up on the page, which seems to happen every time, but we can sort of roughly approximate what the process is going to be. So this is where we are starting. This is our starting point of our process. Let me just move it over, L0 and V1. And we want to get to this side. We want to get to n and vn plus 1. That's sort of where we want to get to. That's our desired level of extraction. So in order to do that, now this bit of the process is actually really, really simple. You draw a line up from here. My pen works. There we go. You draw a line up to here, and that's going to give you your L1. And then you draw another line from L1 back down to your pinch point, somewhere down here. And where it hits the x-axis, quickly draw that in. Where that hits the x-axis, that's going to give us V2. And then you simply just iterate for the rest of it. So you go up again, down, up again, down, and maybe up again one more time, up here. We can see that in total we've got L1, L2, L3. This is really, really rough. I could work through it, but I don't think you can see it very well, so I just want to concentrate on the overall kind of process. L4, and then all the way back down, and you've got, get down here, you've got V5. Eventually, if you do that process enough times. The important thing is to keep on repeating this up and diagonal process until you end up somewhere to the left of this N line, if you like. It's finished. This is sort of like our finish line. So as soon as we get over that line, we've achieved the extraction that we want, and therefore we've got an adequate number of stages. So however many stages you need to achieve that is going to be your answer. And so for simply counting the number of stages, you can see that we've got 1, 2, 3, 4, 5, in this case, 5 stages. So the answer to part E, or whatever it is, part E, that would just be simply 5 ideal stages. Yeah, I hope this helped. I hope this helped clear some stuff up. Good luck for the test and the exam.